Welcome to this lecture in the ongoing series of lectures in real analysis. This lecture is going to be a very short one about a very general concept, and it will mostly be definitions. But let us look at what we did the last time. So last time we defined what is a sequence. So a sequence in X is formally a map from the natural numbers to the set X. But if we write the image of the natural number n as X sub n, then we may denote the sequence as, in a more natural fashion, in this way, or in this way, or simply in this way, and no confusion can arise. And in fact, I can't see how any confusion can arise when we write it like this. Alright, and then we define what's a bounded and what's an unbounded sequence. I don't want to repeat that. And then very importantly, we discussed the notion of a subsequence. So if I just mention the word subsequence and ask you to come up with the definition, most likely you will come up with the standard definition. But let us recall it. So suppose we are given a sequence in the set X. Then a subsequence of this guy is any sequence with the property that there exist strictly increasing natural numbers n1, n2, n3 such that the kth guy in this new sequence is actually the nkth guy in the original sequence. So it is literally a subsequence. Alright, so that's it. And now let us look at the problems. And once you pause the video and solve the problems, we can go to the material for this lecture. So we'll define these two concepts today. What is meant by ultimately and what is meant by frequently. Alright, so let this be a sequence in a set X, and A be a subset of X, be any subset. So then we say that Xn is in A ultimately and I'll put an n here, which I will explain. So we write this, we read it as Xn is in A ultimately over n if there is some natural number. So this is a natural number. I like writing it this way rather than saying that it belongs to n. It looks a little bit ugly to me if I write it that way. So just bear in mind that this is a natural number such that Xn belongs to A for all n greater than equal to n. Alright, so this, the phrase ultimately is well chosen. Beyond a certain point, what this is saying is that beyond a certain point, all the members of the sequence lie in A. So ultimately, eventually, the members of the sequence Xn are all in A, and therefore we write this. And we write a little n here because this little n is supposed to be a dummy variable in this. Sometimes we don't even write this in textbooks, or rather the textbook that I'm looking at does not write this part, but in my opinion one should mention the index over which this ultimately is running. Alright, so let us look at an example. So define our favorite sequence. Let Xn equals 1 by n for all n. Let epsilon greater than 0 and define A as this open interval 0, epsilon. So let me draw a picture. This is 0 and A is, let's say, something like this. So this is epsilon and this shaded part is A. Okay, and let's say this is 1 by 3 maybe, or something, whatever. This is, if this is 1 by 3, then 1 better be somewhere here. Let's say this is 1. Makes sense. Alright, this is 1 by 2. So since we have shown and used this so many times that this guy is equal to 0, we see that xn is an A ultimately. And indeed, I mean, if you just think pictorially, as the denominator increases, so here you have 1, then 1 by 2, then 1 by 3, and eventually you will have all of these guys lying here. So let's say maybe 1 by 100 will be here, and then 101 will be even closer to 0. So ultimately all the points of this sequence will lie in this chosen open interval. A very simple example just to illustrate the definition. Okay, so with ultimately there is a cousin definition of frequently. So again we have a sequence, xn be a sequence in a set X, and A be some subset of X. So it's the same setting, and we say that xn is in A frequently. Over n, again I will put this indexing symbol always, if for all n in natural numbers there exists some little n exceeding that, such that xn is in A. So let's try to understand what this is saying. So okay, so suppose this is your set X and this is A. So what this is saying is that whenever you choose some point of time that okay, this is fixed, there is a time beyond that when xn lies in A, and that's true whenever you choose it. So it's not like xn stops being in A after a certain point. So in other words, ultimately it cannot happen that xn is outside A. It always comes back to A. It may be entirely contained in A. The sequence itself may have the property that all of the points of the sequence are in A. That's also allowed under this phrase. But what this phrase is really telling us is that maybe x1 is in A, and then for a long time all the x2, x3, and these are here. But there will come a time when it will come here again, and there will come a time when it will come here again and again and again. So it basically visits A, the set A, infinitely many times. You can think of it that way. And let us understand this via an example also. So here is an example. Let xn equals -1 to the power n. Then xn is positive frequently. But not ultimately. So note that it is not true. That xn is greater than 0 ultimately. Alright, so this is clear, because for each even number, whenever n is even, this is true. So it of course happens frequently. Just look at this definition. So we have defined frequently Okay. And these examples and just a little bit of thought must have suggested to the reader a certain theorem, if you will. Let me phrase it as a lemma. Is that let xn be a sequence in a set X and A be a subset of X, then one and only one of the following hold. So the first one says that xn is in A ultimately. And the second one says xn is not in A frequently. And both cannot happen simultaneously is also, I mean, so the statement says that one of them will happen and both cannot happen simultaneously. And it is immediately clear that both cannot happen simultaneously, because if suppose the first one happens, then you know that beyond a certain point all the points in xn are in A. So this is automatically ruled out. And if this is the case, then of course this one cannot happen. So simultaneously both of them cannot happen. And in fact, you can show that if this does not happen, then this must happen. Right? Because if xn is not in A ultimately, meaning it violates being in A ultimately, so it should frequently be outside A. Right? If it's not lying ultimately in A, then it should frequently be outside A. So of course this can be proved formally just by following the definitions, and I will leave this as an exercise. This is an exercise in semantics. These are the easiest exercises. Okay. So yeah, I mean there is nothing much more to be said about these two concepts. Let me just make a remark that here we used a subset, and we just talked about ultimately and frequently with respect to subset, but it could be any property. So what do I mean by a property? A property formally is just a function from x to 0, 1. So you can think of this as a true-false statement. Whenever you choose a point little x and capital X, if it maps to 0, you can say that the point x does not satisfy the property, whatever that abstract property is. And when it maps to 1, then you can say that it satisfies the property. And then you can talk about ultimately and frequently with respect to that property. But I can define it, but since I won't be using it, I won't define it. But it's not much different from what we did. Something to keep in mind. Alright, so this is all that I wanted to talk about. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I will see you next time.